Hello, I'd like to go over the pop quiz, in case you are not able to go to office hours or to the review sessions, and have some questions on how the questions were answered. So let's take a look at question number 1. Anytime we're looking at a vapor pressure curve, we want to make sure that we keep track of where we are on the curve. And so that starts off with looking at a generic phase diagram. And since we have two substances, we're really looking at two different phase diagrams superimposed on each other. In this particular problem, there's 3. And then we're drawing a box around that area. That's the vapor pressure curve. So the lines that are coming through there are coming through as a small part of the overall pressure temperature curve. In that case, it's very easy to keep track, or it's much easier to keep track, that the top left corner are going to be liquids. If we're below the line for A, we're at gas A, but we're still in liquid B. And if we're below the line in B, then we have gas A and gas B. And so in this particular problem, we're going to utilize this idea because there's going to be 3 substances. And so if we were only looking at propane and we saw the X there, we would just say, all right, we have gas propane. We then drew only the pressure temperature curve for the isobutane and butane. We would see the X is above those lines, which would be a liquid. So we should have gas propane, liquid isobutane and butane, and that should give us answer B. So B, propane is a gas, and isobutane and butane are liquids. Question number 2 is very similar to the problem we had in the content review. So we see that we have a PEC diagram in which 2 substances are placed. We have propane and butane, and then we have the gases of them. The liquid propane is above butane in the potential energy y-axis. And so the amount of kinetic energy necessary to separate the propane particles and put them in the gas phase is shown by the distance in potential energy. It's smaller than the amount of energy necessary to separate butane from liquid particles to gas particles. That means propane, as shown on here, has a higher potential energy, and butane has a lower potential energy. It takes less kinetic energy to separate the propane, and therefore would have a lower boiling point as compared to butane. So putting all this together, we know that liquid propane is going to have a lower boiling point. That would be the choice between B and C. And then based on that lower boiling point and the analysis of the potential energy, we see that propane also has a higher potential energy compared to liquid butane. So we see the trend that the lower the potential energy is for the liquid, the higher the boiling point. So the answer is C. Okay, question number 3 has in general, we use this problem to think about PEC diagrams, but here we're just trying to order the potential energy and the configurations based on the 2 states we see. So the potential energy general rule is the closer the particles are on average, the lower the potential energy. So gases have the highest potential energy, then liquids, and solids have the lowest potential energy. For configurations, we made the argument that solids have the least, liquids have the next, and gases have the most configurations, or the most options in terms of how the particles are distributed. And so we're looking for the state. The state here to assign configurations is which one is most gas-like, because gases have the highest configurations. And so we see that the undissolved Cl2 in water is going to be most gas-like. It has gas particles, while the dissolved is more liquid-like because all of the particles are inside the liquid phase. So we have two options, that the potential energy is lower in the dissolved because the average particle distance is lower, so we assign the lowest potential energy. And now we say that the lower configurations in the dissolved because it is more liquid-like. More liquid-like, we have less configurations than the gas. So we would pick the answer A. Right, question number 4 was about taking a look at a phase diagram, transitions, and linking it to a delta E versus T curve. So at point A, we're at all liquid, low potential energy. Point B is the liquid-gas interface, which we call boiling. Kinetic energy is constant there. And at point C, we have only a gas, and it's at high potential energy. And it looks like we're heating the gas after that. So overall, A to B is kinetic energy is increasing. At point B, potential energy increases as we separate the liquid particles at low potential energy to gas particles at high potential energy. And then going to B to C, we're just slowly heating the gas, changing the temperature, and so kinetic energy increases. And so on this curve that we're looking at, we just need to identify these pieces. So we see that the first part is a kinetic energy increasing, temperature is changing, so kinetic energy is changing. There's no abrupt change. So in this case, we're going to assign that this is probably A going from A to B. We're slowly heating the liquid. There's then an abrupt change at B as we go from liquid particles to gas particles, a big step. And then B to C is shown there as we're slowly heating the gas, increasing the kinetic energy. So overall, we should be going from A to C. We are looking at we're going from liquid up to its boiling point and then slowly heating the gas to get to C. That is consistent with the curve to the left. The answer is B. Question number 5. This was not on quizzes that were taken on paper, primarily because we just wanted to introduce you to the free answer process and take a look at some of the answers, which we'll discuss on Monday. All students received credit for this answer, even if they took it on paper. So instead of 4 questions, the total quiz was graded out of 5, in which you are automatically given 1 point. Let's take a look at the question. The question is about the change in kinetic energy and potential energy when a soda can is open and the gas that is dissolved in water, like soda, leaves the water at constant temperature. So this is our model. We have CO2 and water, and it's going to be a little bit hard to draw. So I'm going to put a slash through the particles that are CO2 and just round if they're H2O. So before the can is open, we see that we have CO2 particles dissolved into the water. And we have water surrounding them. And then what we do, this is the before picture, then we open the can, and all of the CO2 goes up into the gas phase, and the water itself, it doesn't contain any CO2. That's the case where the soda seems flat, or we say it's flat. And so we want to know what happened to the potential energy and what happened to the kinetic energy. Well, first, we made this a little bit simpler than maybe we needed to, but kinetic energy is constant because temperature is constant. Anytime we say constant temperature, it's going to be constant kinetic energy. But the potential energy has changed. It is increased as we have more particles in the gas phase when it's open than we did when it was closed. So in this case, we should have kinetic energy is constant, potential energy increases as we take liquid particles of CO2 that were at low potential energy and take them up to the gas phase, which has high potential energy. Right, so these questions represent some very important ideas in Unit 1, Module 2. These will repeat. They will be present on the exam. We will also have Unit 1, Module 3 questions. So it's really important to take a look at these questions, and if you have any doubts or any further questions, you can email me or you can come to office hours next week on Wednesday where we have an exam review. All right, good luck everyone.